Good morning, dear students. Today we are going to continue the remaining portion of nucleic acid chapter with the heading Structural Organization of DNA. This was put forward by Watson and Crick. Watson and Crick elucidated. They explained the structure of DNA for the first time. And the DNA that they describe is of bDNA. bDNA. Why we are mentioning about bDNA? That means DNA exists in different forms, different variants of DNA are present. Among them, the Watson and Crick explain the structure of bDNA. So we are going to see their description about the bDNA point by point. Whatever the type of the DNA, each DNA consists of two helical polynucleotide chain. This is common for all different types of DNA. Two helical polynucleotide chain. So let's see. First point in their description regarding bDNA. Uh, the DNA is a two helical polynucleotide chain. One is this one and the other one this. Two helical polynucleotide chain is coiled right-handedly around a common axis. Axis is passing through this way. This is the central axis. And around this axis, two helical polynucleotide chains is right-handedly coiled to form a double helix. Clear? Okay. Next, as a result of this coiling, there exists a major groove. Major groove means this portion. This major groove is there. Its depth is 8.5 angstrom and its width is 12 angstrom. And also a small groove also there. A major groove and a minor groove is there. What about its measurements, its different measurements? Its depth is 7.5 angstrom and the width is 6 angstrom. Why this major groove and minor groove exist in this DNA double helix? Why can't it be of same type? There is a reason that we are going to see next. What is the reason for the existence of a major and minor group? This is a cross section of one DNA double helix. This is another DNA double helix. You need to listen only to this picture now. And up to here, this is one strand of the double helix and this one is another strand of a double helix. And this is the purine base and this one is a pyrimidine base. We know that the bases are bonded. Which type of bond? Glycosidic bond is there. Glycosidic bond bonded to which group? Sugar group is there. Sugar. And that sugar is again connected or bonded to a phosphate. Then sugar and phosphate form the rail or it form the structural framework that is represented by this line here. So coming to here, you look on these two bonds. One glycosidic bond is here and another glycosidic bond is here. And we know the significance of this bond. With this bond, the bases are connected to the sugar. Then you need to listen about its position. As we consider it as a circle, this is the diameter. And look, the position of this glycosidic bond, it is not in perfectly opposite side with regard to the diameter. Its position is somewhat below the plane of the diameter, not in a diametrically opposite side. That's the reason why the existence of a major groove and a minor groove. Its position is not convenient to have a same type of groove. Okay, that's the reason. Then some other points also here. Uh, Here is an oxygen and here is the nitrogen. This oxygen of the pyrimidine and this nitrogen of this purine is located to the minor group side, and that of the methyl group of the pyrimidine is located to the major group side. And along with that, a bonding is very necessary between these bases. As we know, it's the hydrogen bond. So a hydrogen bond donor is there and an acceptor also there. It is bordering the that base pair or the major group side. So hydrogen donor is there and a hydrogen acceptor also there. That's about the reason. Main reason I already explained, because because of the unsymmetric. It means it's not perfect opposite side with regard to the diameter. That's why the major groove and minor groove is present. And also you need to look that minor groove is always located or faces against a major groove. So that's the arrangement. So reason is very clear now. Then this major groove, there's another significance for this major groove region. What is the significance? It is more accessible to the interacting proteins, because from the DNA is very necessary to transcribe proteins. Proteins, which are proteins means that may act as enzymes that involved in many metabolic pathway or some other products. So anyway, for that process, many enzymes and other proteins need to interact with the DNA. That interaction is usually more oftenly happening in this major groove region. And this double helix is called plectonymic coil. Why is it called plectonymic coil? Because that coiling is interlocked around a common axis. That's why this coil is called plectonymic coil. And also this each strand or the double helix is anti-parallel. Anti-parallel means this strand ends with 5' and this strand ends with 3', not the same one. That's why it's called anti-parallel. And also some more other things we need to understand here about this anti-parallelity. That is, in one strand, the oxygen of the sugar moiety faces the upwards, while in the other strand, the oxygen in the sugar moiety faces downwards. That I will show you. This is one strand and this is another strand. And look here, the oxygen of the sugar moiety is facing upwards, and in the other strand, that oxygen of the sugar moiety is facing downwards. It's very clear that uh, orientation of the two strand is towards opposite direction, anti-parallel. So that is another feature, anti-parallel property of the two polynucleotide chain. Then complementarity. Complementarity is another feature of DNA. Complementarity is very clear that we know that this is one strand and this is another strand, and suppose it is adenine, if it is adenine, it can only bond. This is not adenine because here three bonds are there. So we are going to understand that it is guanine. Guanine base is there and it pairs with only cytosine. If it is of RNA, it can pair with the uracil. It can't pair with the thymine. So that pairing is very strict. Uh, by understanding the sequence of bases in one strand, we can predict what would be the sequence in the other strand. It is complementary. Is another feature. Some reason, there are two reasons for having this complementarity feature for the DNA double helix. Let's see that. That is a steric factor and a hydrogen bonding factors that we are going to see. What is steric factor? This is the chemical structure of ADNA double helix double strand. This is one strand and this is another. And here phosphorus is there, sugar is there, base is there. Look, the distance, these two distance between two glycosidic bonds. We know that glycosidic bond is the bond used to connect the sugar with the base. Here is one bond and here is another bond. So distance between the glycosidic bond throughout the helix is same. Distance between glycosidic bonds are same. So, and what's that distance? It is 10.85 angstrom unit. So, it's very logical, it's very clear, simple to understand that it is not possible to incorporate a a purine against this purine. This, we know this is a purine and against this, there is only this much space. Pyrimidine have only one ring, but in the case of purine it has double ring there. So if we are trying to insert a purine in this place instead of this pyrimidine, then that space is not suitable, it's not convenient. That's why it's only possible to pair a purine always with a pyrimidine and also a pyrimidine always with a purine, because the space is such a type, solely supporting that type of arrangement, that type of stocking, that type of pairing. So that is one reason. And also that angle angle of that bond between the line joining the first carbon and that base, that angle is same for all the glycosidic bond. For all the glycosidic bond, here is one bond, here is another bond. So that angle, this angle, this angle, and this angle all are same. That's another reason. Then I already explained this point. There's insufficient space for incorporate two purine or two pyrimidine. Only possibility is to incorporate one purine with the pyrimidine or one pyrimidine with the one purine. That's the steric factor. Then hydrogen bonding factors are also there. Has well-defined position for forming hydrogen bond. Adenine and thymine. Look here, it's only convenient to form two bonds. There's no provision or a convenience to form a third hydrogen bond. Only two bond is possible. But in the case of guanine, look, it's possible to form three hydrogen bond is there. So that's about uh, hydrogen bonding factors that also support the complementarity property of DNA double helix. Okay, next, um, second point. the position of phosphate and deoxyribose units. Look here, the phosphate and the deoxyribose as a sugar, that is the periphery of the helix. They occupy the periphery of the helix. At the same time, base pairs are in the centermost position. We can compare it to a staircase, right? And the plane of the base pair is somewhat perpendicular to the helix axis. Its position is somewhat perpendicular. Perpendicular means we know that in this way against this line. And coming to the third point, diameter of the helix. Diameter of the helix means this distance, this length. In this points, I am giving the measurement in two units, nanometer and angstrom. You only need to follow any one of the unit. Otherwise, it may lead to confusion. So it's better to follow the angstrom measurement itself. So I am giving more stress to the angstrom measurement. So diameter of the bDNA helix is 20 angstrom, and distance between base pair along the helix axis, that is this distance is 3.4 angstrom. This distance is otherwise called RISE, RISE. Okay, so distance between the base pair, it is 3.4 angstrom. That distance is otherwise called RISE. Then bases related by a rotation of 36 degree. That means as it coils around, as the DNA double helix coils around, uh, this base pair has a twist with regard to this one with an angle of 36 degree. A tilt, an inclination or a twist is there. Its degree is 36. And the other base pair also is twisting with an angle of 36 degree with regard to the former base pair. That's the base relation. Its rotation, it's anchored. I think this point is clear. I'll show you that. 36 degree of twist along the helix for each base pair. Each base pair is showing a twist, a gradual twist of 36 degree. That's what I'm explaining here. One helix turn contains 10 base pair. Look in this picture. And before understanding this point, we need to understand what is one turn. One turn means we can consider it as from the beginning of one minor groove to the beginning of next minor groove, or from the beginning of one major groove to the beginning of next major groove. So here this is one turn. This is one tone, beginning of one minor groove to the beginning of next minor groove. This is one turn. In this turn, one helix turn, how many bases? That is, it is 10 base pair. We can count that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 base pairs are there in one helix turn. And its length is 34 angstrom. Its length is 34 angstrom. That length is otherwise called pitch. P-I-T-C-H. Pitch. Helix pitch. Helix pitch means also this length. Then fourth point regarding the bonds. We know that's very clear that between the bases hydrogen bonds exist. If we consider hydrogen bond individually, we know it is very weak bond. But as so many hydrogen bond exist throughout the helix, then that gives some stability or strength to the structure. And also along with this, van der Waals force also there. Van der Waals force means it is a type of weak force that exists between intermolecules. Intermolecules. So weak force exists between intermolecules. Where it is usually, where it is acting. It is acting between the stacked bases. This is one base pair and this is another base pair. They stacked one above the other, and between the stacked base pair, which force is acting? Van der Waals force, and it gives stability to keep the structure intact. And regarding the pairing, always adenine can form only two hydrogen bond with the thymine. Guanine at the same time can form three hydrogen bond with the cytosine. Why is it so? I already explained to you in the former slide with the figure. The complementary, one strand is, the base sequence in one strand is complementary to the next strand. Fifth point. The sequence of bases in the strand determines the genetic information it carries. The base sequence, precise sequence of bases, that itself carry the genetic information. And the whole structure just like a winding staircase with the sugar and phosphate form the railing, and the base pair form the steps. And 6 point, it's already told you. So orientation of two DNA chain is anti-parallel. This is all about the Watson and Crick model of DNA. That's about BDNA. BDNA. So I'm not again going to explain in this portion, because next portion is the structural features of A, B, C and Z DNA. That is variant forms of DNA. BDNA, regarding BDNA, I already explained to you. Here in this section, I am going to explain to you only about ADNA, cDNA and zDNA. So that's why it is written here. Classic Watson and Crick model is BDNA. It's already finished. Then we are moving to ADNA. What is ADNA? ADNA means it's not a separate different type of DNA, but it is forming from the normal BDNA because of certain situation, a change in the environment that result in the formation of ADNA from BDNA. What is that situation? What's the condition? Under dehydrating condition. If dehydration, is no water molecules that is enough to form BDNA conformation, then what will form? The BDNA change to another conformation, that is another form, that is ADNA. It's very rare. Okay, and its lengthwise and size-wise, it is very short and compact. So it's very simple to understand that if we take a BDNA and we are compressing it from its top, what will happen? Its length will decrease. Its length will decrease. Understand? Oh, that's the same thing happening in the case of ADNA. It is discovered by Rosalind Franklin. Important structural features. It is much wider and flatter than BDNA. Why is it so? Because it is compressed from its top. As we compress anything, its width will increase. Okay, I will show you the picture of ADNA. Look here. This is the BDNA. It's somewhat more stretched than this one. This is more compressed. As compression is here, so its width also will increase. Um, then it is similar to BDNA in the in aspect that it also right-handed helix. It is also a right-handed helix like BDNA. And the helix diameter, here ADNA and BDNA is there. Helix diameter means this diameter is 26 angstrom. Then the helix pitch means height of one turn or length of one turn of ADNA is 28.6. That means it's shorter when compared with the BDNA. Then ADNA is 20 to 25% shorter than BDNA due to the small rise pattern. Okay, it's clear. Its length is already shortened because of that compression. That's why it is shorter than BDNA. And also because of the small rise per turn. Small rise per turn means small distance, small gap between the stopped base pairs. That also a reason. As the space is less, that itself make it very clear that the base space, number of base space in one turn will be more when compared with the BDNA. So ADNA has 11.6 base space per turn because this distance is less when compared with the BDNA. Distance between adjacent base pair is 2.9 angstrom. Then helical twist, that twist with respect to one base pair. Twist with respect to, what is twist of this base pair with respect to this base pair is how much? 31 degree. And if we take a cross section here, we can see an axial hole in the center of this ADNA. And see how the DNA base pairs are arranged in both these two types. Here it is somewhat perpendicular to the helix axis, but here is in an inclined way. So an inclination is there. So the DNA base pairs are inclined to the helical axis. And also regarding the major and minor groove also difference is there. ADNA has narrow and deep major groove. It is narrow, not wide as BDNA because it is compressed. That's why that groove become narrow. While the minor grooves are wide. At the same time, minor groove become wide and but shallow. Then next point, the deoxyribose sugar puckering. Puckering means wrinkling. That sugar moiety, we know that sugar moiety is present in the double helix. That sugar moiety has a wrinkling. Because of that wrinkling in ADNA, that wrinkling is of C3 endoform. But in the case of BDNA, that puckering, that wrinkling is C2 endoform. That we are going to understand what is C3 endoform and C2 endoform. I will show you a picture. This is the sugar and this is the phosphor moiety, and this is ADNA's sugar phosphate group. Look here in this picture, the third carbon is out of the plane. So, in the case of ADNA, it is C3 endo conformation. The third carbon is out of the plane. But in the case of BDNA, the second carbon is out of the plane. That is C2 endoform. So, I think now it's clear what is C3 endo and C2 endoform. So, deoxyribose sugar puckering, that wrinkling in ADNA is C3 endoform and that of BDNA is in C2 endoform. Then conformation of glycosidic bond in ADNA is antiform. That of BDNA also it is antiform. Then what we need to understand from this antiform of glycosidic bond? We know that glycosidic bond is that bond used to connect that base with the sugar. That bond can rotate with respect to that sugar. We'll show you that. This is the sugar and this is the base, and this is the glycosidic bond. Sign orientation and anti-orientation is here. Sign orientation means here that bond is rotating only 60 degree. And listen here, that group is that functional group is on this side. As moving to the other orientation, anti-orientation, here that bond, glycosidic bond, rotate more. 240 degree it rotates. Because of that, this group comes in the opposite side. This is the anti-orientation. Only need to understand what is sign orientation and anti-orientation of glycosidic bond. For ADNA and BDNA, the glycosidic bonds orientation is anti. Then we are moving to cDNA. So ADNA is over, BDNA also over. Regarding cDNA, when this type of DNA is forming out of the BDNA, what condition forced it to become a BDNA to a cDNA, normal DNA to occur this cDNA form? When the humidity is 66% and also there is lithium ions. Lithium ions is there, and also humidity if it is 66 percentage. Under that circumstances, what will form? cDNA. DNA exists in cDNA form. Uh, Picture I will show you. This is the cDNA, somewhat similar to bDNA itself. I'll explain. It is also a right-handed helix. Then axial rise. Axial rise means distance between base pairs. Axial rise is already explained. Here you can see that distance between, this is one base pair, this is another base pair. That distance between the base pair, it is called axial rise. It is 3.32 Armstrong per base pair. And base pair per turn. In one turn, how many base pairs are present? 9.33 base pairs. And what about helix pitch? Helix pitch means height of one turn. It is 30.97 Armstrong. Then rotation per base pair. What is the twist of one base pair with regard to next one? It is 38.58 degree. Diameter of the helix is 90 Armstrong. And the tilt of base pair with regard to the helix axis is 7.8 degree. And this cDNA is smaller than both aDNA and bDNA. Then we are moving to next step, ddNA. This ddNA is not mentioned in your syllabus. Even then I am explaining, pointing this DNA, this DNA also along with your topic, because it's an additional point. If you add this point along with your answer for the examination, it will make you to grab more marks for this question. So that's why I am giving this type of variant DNA also here. Its feature, it is very extreme, it's very rare, extremely rare. And in this type of DNA, in one helical turn 8 base pairs are present. And what's the distance between base pair? Axial rise, it is 3.03 Armstrong. And the tilt of one base pair from axis is 16.7 degree. Where it is found? In DNA, such DNA molecules that are devoid of guanine. Guanine deficient DNA exists in ddNA form. Then coming to the last one, that is DNA. When the DNA accuse this DNA form uh, under high salt concentration. When the salt concentration is high, then that situation DNA exists in DNA conformation. Uh, then it is left-handed. That is very important. All the other types are right-handed. This is left-handed and is left-handed conformation, and also the bases are arranged in a zigzag pattern. It is very easy to understand the difference from bDNA. If bDNA, if we take and rotate against the right-handed direction, and also if it is stretched, then it can occur this conformation. It is discovered by Andrews Wang and Alexander Rich. Where it is located? It's located, this type of DNA is seen in the upstream position or the beginning position of a gene. So that itself indicates that this is a DNA have some role in regulation of gene expression. Because during the time of gene expression means the transcription of a particular gene. During that transcription, it has that is a DNA has some role in regulation. That's what. Then next, structural features. It's the helix diameter of DNA is 18 Armstrong, and the total height of a helix turn is 44 Armstrong because it is stretched one. Then nucleotide pairs in the DNA occurs as dimers. Dimers means, I will show you here. As a picture, this is a picture. Base pairs are here. Instead of bonding, we are here. Base pair in one strand make covalent bond with the base which is nearby. In such a way, it can form dimer. The base of this strand form bonding with the base that is very near to it, neighbor base. That type of bases that having bonding with the nearby base, it is called dimer. I think it's clear. Okay, so nucleotide pairs in zDNA occurs as nucleotide dimers. Now, each turn contains 12 nucleotides. Each turn contains 12 nucleotides because it is stretched form of DNA. That's why more nucleotides. The helical turn per base pair, that rotation is 9 degree for pyrimidine to purine step. That means a pyrimidine base pairs with purine. In that step, its rotation is 9 degree, and 51 degree for if a purine binds with the pyrimidine. So there that twist is of 51 degree. And in the case of DNA, major groove is more flat, but minor groove is narrow and deep. DNA has a solid core. It's not a hollow core. I will show you that. Similar to something like this, DNA also has a solid core in the center. Solid core at the center, and the sugar pucker. Sugar pucker means that folding of sugar moiety is C2 endoform for pyrimidine, but that of purine, that puckering is of C3 endoform. Puckering also I have already explained to you. Then the glycosidic bonds conformation is anti for pyrimidines and sine for purines. So both type of conformation and both type of puckering is present in zDNA. Okay. Then regarding the stability, it's very unstable. It's a transient structure, and so it may soon quickly disappears. So it's very difficult to learn or study about DNA extensively. So it's a table showing all the features, all the important points regarding the DNA and its comparisons with respect to each type. It's very important. You need to learn this table along with writing that answer. You can add this table also depending upon the marks. Condition: how when ADNA exists 75% relative humidity in the presence of this type of ions, and BDNA occurs when 92% relative humidity, more humidity, low ion strength, and cDNA when 60% relative humidity, and also lithium ions is there. zDNA high salt concentration. Shape is the broadest because it is the compressed one. This is intermediate, and this is the narrowest. Then this is the narrowest, most stretched one. Then helix sense, it is there. All these are right-handed except zDNA. zDNA only is left-handed. Helix diameter for ADNA it is 25.5, BDNA is 23.7, and cDNA 19.0, and zDNA is 18.4, because BDNA this is a normal type 23.7. Usually occurring DNA is of this type. It has a helix diameter of 23.7. But coming to A, it is compressed. That's why it has more diameter than the BDNA. Coming to both these types, cDNA and zDNA, these are stretched form. That's why the diameter is less when compared with the BDNA. Rise per base pair means distance between the base pair. As it is compressed, it is having the least rise, 2.3 angstrom, and BDNA has 3.4 angstrom, cDNA 3.32, and here zDNA is more stretched, is having 3.8 angstrom. Helix pitch length as it is compressed, it has the least helix pitch 25.30 angstrom. For bDNA, it is 35.36 angstrom. For cDNA, again it is 30.97, and it's the most stretched form. So that's why 45.60 angstrom, 60 angstrom. The rotation per base pair, rotation of one base pair with respect to other one, is 32.72 for this one, 34.61 for bDNA, 38.58 degree for cDNA, and minus 60 degree for or is a DNA. Base pair tilt with respect to the helix axis 90 degree for this one, and for bDNA 1 degree, for cDNA 7.8 degree, and ZDNA it is 9 degree. Glycosidic bond, its orientation is anti for these two. For this time it's not mentioned, and for ZDNA both type conformation is existing. Major groove is narrow and very deep for ADNA. It is wide and quite deep for pDNA. It's not mentioned, but it's flat for ZDNA, major groove. Minor groove with regard to ADNA is very broad and shallow. It is narrow and quite deep. It's not mentioned, but for ZDNA, minor groove is narrow and deep. With this, we finish today's class and section. Thank you.